So now just briefly, we'll move on to gas coolers. Okay, so maybe you've noticed the trend more recently is to install in the retail sector and wherever else possible CO2 systems, but more specifically transcritical CO2 systems. So every transcritical CO2 system's got a gas cooler. And the norm there is to use stainless steel tubing. And the reason is simply the high operating pressures. Okay, so what is a transcritical system? That's a question I hear a lot. What's a transcritical system? Okay, you remember that our introduction, the pH chart. You remember the critical point. Okay, so a transcritical system operates above the critical point. So you take your pH chart for your CO2, you find the critical point, you have to know that your system's going to operate above that. And the transcritical point is obviously for, in this case, if you look at that corner of your pH chart, that's what your basic diagram looks like. So you see it's very similar to the standard DX system, but your operating, but your high side pressure is above your critical point. That's the main difference. So it's not, you know, I think if I have to simplify it, just try and, look at the simple version before you move on to the more complex versions. Okay, so there's your critical point, and your critical point is 31 degrees C. So if your ambient is 42 in Paul, can you condense with the ambient air if your critical point is 31 degrees C? The answer is no. If your system is going to exceed 31 degrees C, it will be operating above the critical point. So hence the term transcritical. All right? So, but of course your system is very often functioning like now. It's cooler. Your system, your ambient air is colder, so your system is going to operate below the critical point. So you have most of these systems have a very good rack controller, electronic rack controller that controls that, measures the conditions on site and the result, and then decides run the fans harder and get us below the critical point. And then of course for the greater part of the year, your transcritical system is operating below the critical point. Okay, and then your diagram looks very similar to what we started off with. Now, if you go back to the pH chart and the cycle on the pH chart that we started off with, it's very similar. The difference is, however, you see there on that end, you don't end up with saturated liquid. So the way your system works is, you have that line at the top there in the transcritical zone. Again, what does your gas cooler do? Your gas cooler changes the temperature from a high temperature over there all the way that way, and it reduces the discharge gas temperature. It does not condense. It removes as much heat energy from that discharge gas as possible. Then it gets to an HPV valve, very similar to an expansion valve, and then you have a sudden drop in pressure. And as you get that sudden drop in pressure, you cross that saturation line. And what's underneath this saturation line? It's liquid plus vapor. Then you have obviously a more complex systems where you have a medium temperature circuit and a low temperature circuit, and they combine. But same rules still apply. At the top there, you need to reject that heat energy. Okay, so that line at the top is a line you need to control very accurately. So hence you will see every gas cooler comes with EC fans for the greater part. I've seen people apply all kinds of gizmos to change fan speed, but basically you want to keep that line at the top as stable as possible. You don't want it fluctuating, you can't stage fans. So what you need there, you need to pick a set point and you need to maintain it. And you do that with EC fans. Okay, so and you don't stage the fans. They all run simultaneously. The benefit then is you draw air across the entire gas cooler the whole time, but your EC fans can go down to, I think, about 5% of their maximum speed. Okay, so your EC fans is a crucial component here. EC stand for electrically commutated, I think. You could have variable speed drives, but then you don't get the full range. No? So think about it, 50 hertz down to, 5 hertz. That's a very big range. And of course the EC fans also move more air. So the cat's getting hungry. All right, back to that diagram. So in very basic terms, the CO2 system, what's the difference between a transcritical CO2 system and a normal DX system? Is you have high side pressure, low side pressure, but now also an intermediate pressure. So that's the thing that got added. So the benefit you have, if this is new to you today, is that all of this was refined in the last 10 to 15 years. It started off far more complex than this. So this is very simple in what it was when you compare it to what it was 10 to 15 years ago. So again, there's your gas cooler, there's your HPV valve, you have your sudden drop, there's your HPV valve, you have your sudden drop in pressure, you cross that saturation line, there's your liquid receiver, just like any liquid receiver, what accumulates in the bottom of the receiver? Liquid. What's on the top of the receiver? Vapor. The liquid you feed to your expansion valve, and your expansion valve works like any other expansion valve. It's an electronic expansion valve, but you need to feed it with liquid, and then the rest is exactly the same. Then you have that receiver, and you have a valve there that checks. If the pressure gets excessive, remember you need to reject the heat there with your gas cooler. If it's an extremely hot day, maybe conditions you didn't cater for, and the pressure in the receiver gets excessive, that valve opens, lets it through into the suction side of the compressor. So it really is not as intimidating as I think a lot of people believe it is. Just pay attention, read what you can. There is mountains of information on the internet. But yeah, it all starts off like that. So hopefully that helps a bit. But your gas cooler operates as a condenser for the greater part of the year. There's a few hours in the year where it operates transcritical. And that's why the system is called transcritical. The benefit is when it's subcritical, your COP is really good. But when it's transcritical, the COP is not so great. If you compare it with an HFC system, then you could argue, yeah, the HFC system is better. Yeah, but 80% of the year the system is going to operate when it's dark and cold and winter, when the wind is chilly, then that COP is significantly better. So you have to look at energy consumption and COP across the span of a year. I think Wynand Groenewald is really the expert at that. I've seen some really good research from him, but basically the long and the short is you can't compare the two when the CO2 system is operating transcritically. You got to look at across the realistic operating hours in a year.